Okay, guys, we're back again. Hopefully you can see and hear my screen. I'll get rid of this. Get this out of the way. I'll get this. Okay, type into the chat box there if you can see and hear me. I'm recording again. Okay, great. Thank you very much. So it took a few extra minutes here because we were having such a good time here without you people. So
Don't tell them I
let me finish. Let me go back to this problem with the the chicken feed and the mean weights for the different kinds of chicken feed, different 6 or 7 different categories of chicken feed. I made up another variable here, which is 1 represents horse beans and 2 represents linseed and so on and so forth. Analysis of variance likes to use numbers rather than I think there's a little bit of a problem with it here. That should be a 3. Let's see, 2, 3. Let me just make sure that this is right. Yeah, I have an extra 1 in here. Should have been 6, but that's okay. It's all right. This will work fine. Okay, so at any rate, so I want to. Oh, you don't see anything up there. Oh, I got to relog in, I guess. Yeah, that's right. Should do. Fox protocol. Actually, no, I could have probably just gone back. Hang on there, guys. I'm just getting the overhead screen set up back here. I hate doing this because I keep fearing that one of these days I'm going to forget my real name. Way. Yep. This is done. Yep. 20 steps. Oh, it means in a different browser. That's why it looks different. Okay, we're back again. All right, sorry about that. Okay, so we were looking at analysis of variance. So before we broke for a break there, I went to analyze, compare means, one-way analysis of variance, and I asked SPSS to show me compare the amount of weight gained by these chickens based on the various different kind of feed that they were fed. Okay, 1 represents horse beans, 2 represents linseed, and so on and so forth. So I'm going to go ahead and run this calculation and see what SPSS does for me. Okay, so this is the analysis of variance. Come up is pretty straightforward, little box here. But let's figure out what these numbers mean. If you play the video that's online where you do this, you do the exercise using Excel, and then you repeat it using SPSS, that'll give you a pretty good idea on where these numbers came from. To make a longer story shorter, these numbers represent the sum of squares, the variability between the means of the groups. In other words, this is the sum of squares. Remember, we took when we did standard deviation in the beginning of the semester and variance in the middle of the semester. We took the sum of squares, we divided it by the sample size minus 1, and we called that the variance. Okay, well, this is exactly what's happening here. This is basically the sum of squares of the differences between the means. Now, notice that there's 6 degrees of freedom, which means that there's 7 groups here, right? So we looked at those 7 groups, and we took the means, calculated the differences between each group's mean and the average for all the groups, and we found that the sum of squares, when we squared the differences, came out to this number divided by the degrees of freedom, gave us a variance. In this case, they happen to call the variance mean squares instead of the mean square instead of the variance. Okay, we did that within the groups. In other words, we looked at every value within the group, within the groups, and in this case, since there were 6 or 7 groups, there was really I guess 70 chickens in this thing. So it's 70 minus 6 groups is 64 degrees of freedom. This is the sum of squares within the groups. In other words, the difference between each value in each group and its mean within that group. In other words, not outside of the group, but within the group, right? And then divided by the degrees of freedom. And this is our mean squares within the groups. Okay, so what do we need here? What we need here is in order to be able to tell that the means of these groups are different, we need the means to be far apart. In other words, the mean squares to be a big number. And we need the variability within the groups to be narrow. We want the groups to be the means to be far apart, but we want the groups themselves to be a narrow spread. The narrower they are spread, the better off we are. The wider the means are apart, the better off we are. So we create a formula, which is the mean squares between the groups divided by the mean squares within the groups. We take that number divided by this number, and that gives us an F statistic. That's our analysis of variance statistic. Now, based on the degrees of freedom, that F statistic has a critical value. We can actually go to a table and look up for the number of degrees of freedom what that F statistic has to be in order to reject the null hypothesis. Let me see if I can't find that.
So it's the mean squares between the groups divided by
the mean squares within the groups, right? Okay, and I'll show you that in a second. Krusty. Here we go. Okay, so if this is our table, you'll notice that these numbers go very high. These are the degrees of freedom within the groups. That's the individual chickens in this case. And this is the number of groups. So degrees of freedom from the number of groups. In other words, 7 minus 1 or 6. So it's 6 degrees of freedom. And I think the degrees of freedom within the groups was 64. So let's go to 60. So the critical value for analysis of variance is 2.25, right? If we only had a couple of groups, if we only had 3 groups and the relatively small, let's say relatively small sample size, it might be 3.48, right? Or 4.35 and so on and so forth. So based on the samples, the number of means, number of groups, and the number of people or subjects within the group, you decide what your critical value is. Our critical value looks to be something like 2.25 based on 6 degrees of freedom between the groups and 62 degrees of freedom within the groups. Okay, so you can see that I went way beyond what I needed in terms of my F statistic. It's much bigger than 2. And as we would expect, our significance, p-value, our significance is less than 0.05, so I can reject my null hypothesis. Well, what was my null hypothesis anyway? Okay, let's take a look at that. Okay, so for analysis of variance, what we're saying is that we're going to compare many means at the same time. So our null hypothesis is that the mean for group 1 is equal to the mean for group 2, is equal to the mean for group 3, is equal to the mean for group 4, is equal to the mean for group 5, etc., etc., right? In this group, each mean represents the average weight for the birds that ate that kind of food, right? So we haven't tested every bird in the world. We just tested this one's in our sample, right? So our alternative hypothesis. Now this is where it gets a little tricky with analysis of variance. Okay, for you to reject your null hypothesis, you don't have to have all of these different. You only need to lead at least two of them to be different. So in other words, the alternative hypothesis is not all of the means are the same. Right? At least two of the means are different. Another way to express that, at least two of the means are different. I noticed that some of you guys already started working on this on homework, and you were pretty much understanding this, I think. So at any rate, so that's the deal here. So in this case, we could reject the null hypothesis and accept the alternative hypothesis. Except now we got a little bit of another thorny problem. Let me just bring this, I closed the output table there, so I need to do this again. Descriptive statistics, explore. I'm going to look at all the different kinds of feed and see how they differ. I know that at least two of these means are statistically different. I can reject the null hypothesis that they're the same. And if I look at the box plots, you can pretty much see, well, this one looks definitely different than this one. But now this one looks like it's different than this one, but these two maybe not, because they kind of overlap a lot, and the means and the medians and so on and so forth. Well, I need to figure out which of these are really different. I know from my result that at least two of the means are different. I can reject my null hypothesis that they're all the same. Well, now I have to go a step further. I have to do a test after having shown that the analysis of variance, I can reject the null hypothesis. I have to do a post hoc test. Post hoc means is Latin for after the fact, right? So I'm going to go to analyze, compare means, analysis of variance, analysis of variance, just as I did before. I'm using VAR, that variable that I created, which is just a numerical version, because it doesn't seem to want to use the text version of this. And I'm going to go into here, post hoc test. Okay, in post hoc test, now we have a number of different options. We went over this on some of the videos, and I think last Wednesday, I think we went over a bit of this. We have a number, these are all based on different kinds of reasoning to determine whether or not individual means compared to each other are different. Which of the means in these groups are different? The most common ones that people use are Bonferroni and Tukey. Bonferroni is a relatively rigorous test. Okay, you could use more than one version. You might get slightly different versions of it. The reason that you would choose one over another has a lot to do with the type of data that you're analyzing. For our purposes, let's stick with Bonferroni for what we do. It's a relatively rigorous test, and it's hard to go wrong with that particular test. So we're going to use Bonferroni. I'm going to click continue and click OK. It's going to repeat the analysis of variance test, except in addition to this table, now it's going to give me a table where it compares every one of the groups to every one of the other groups. So let's see what I have here. I have group 1. I should have coded this, I guess, so that you could see which food was which. Group 1 compared to group 2, group 1 compared to group 3, group 1 compared to group 4, 5, 6, and 7. So if I go over here, you'll notice that for each comparison, I have a significance, a p-value, a probability of being wrong if I reject the null hypothesis that the means of the two groups are the same. So when I'm comparing 1 to 2, it's not less than 0.05. I can't claim that they're different. I can't reject the null hypothesis. But I can say group 1 versus group 3, whichever feeds they are different because less than 0.05. Group 1 compared to group 4, no. Group 1 to 5, group 1 to 6, group 1 to 7, I can say all of those are different. Well, then notice it goes through every possible combination of comparison. It's comparing group 2 now to group 3, group 2 to group 4, group 4 to 5, and so on and so forth. So you can see if group 2 is different than so on. But notice that some of these analyses get repeated. Group 2 compared to group 1 is the same as group 1 compared to group 2. Fortunately, you'll notice you get the same result. So it doesn't matter which direction. So SPSS does every possible combination of this. So now,
sorry, it was analyze and then compare means.
Yeah, I'll go back. I'll repeat it. So you can compare all of these different possibilities to one another to decide. Well, group 4 is statistically different than group 7, but not statistically different than any of the other groups, right? And you'll notice you get the same result if you look at the other comparisons. Compare group 5 to group 7. Well, you failed to reject the null hypothesis, right? Group 6 to group 7. So it only works 4 to 7. So you can go through this and evaluate for every different kind of feed compared to the other. If you had done this with a t-test, it would have taken you forever and would have increased your probability of error when you reject your null hypothesis. Okay, so this is kind of this gave you kind of like a kind of heart-wrenching chart here. It's a lot of variables, a lot of different values for the type of food that they're using. But it works whether you use if you take a look at that simpler example that I did in the video, which I repeated, which I put in the folder for this week's class as well. That only has 5 values inside of 3 groups. It's a much simpler example than this is. But this is the way you would work it out if you had Excel. So if you got this table and I asked you if you could reject your null hypothesis, if I asked you to assemble a null hypothesis, you would say, oh, it's 7 groups here. So mu1 equals mu2 equals mu3 equals mu, and so on. Alternative hypothesis. None of the, at least 2 of the means are different. And could you reject your null hypothesis? Well, yes, you can because of the size of your F value and how small your significance is, your P value is. Probability of being wrong if you reject the null hypothesis. And then if I showed you your multiple comparisons or your post hoc test, well, then you could say to yourself, if I asked you, is there a significant difference between the amount of weight gain for chickens that were in group 8 to feed in group 1 versus group 5? You'd say, oh, group 1 versus group 5. That's less than 0.05. Yes, there's a statistically significant difference in the amount of weight that they gained. Okay, so you could actually look at the individual outcomes then too as well. Okay, so I want to go back to looking at our exam, our homeworks. And I just want to run through number 5 again. Yes.
Because that post hoc is not working for me.
Analyze.
Yeah.
Okay. Analyze. Descriptive statistics, right? I'm sorry, compare means, one-way analysis of variance.
Right.
Okay, so, oh, I opened the wrong file here. I have more than one file open here. Chicken feed. Analysis of variance, compare means, one-way ANOVA. Okay, did you put the weight in here?
Wait, yeah, well, I'm going back. Compare means one-way ANOVA. The dependent list was weight.
Okay, and then the factor.
Yeah, the variance.
Okay, and you clicked, and in post hoc you checked off Bonferroni?
Yeah.
Okay.
And then that's it. But mine's not working.
Oh, you didn't get that table?
It says post hoc test did not perform for weight because at least one group has fewer than 2 cases.
Oh, you know why? There's a problem if you go into the data file. I don't know if you noticed me doing this before I did the test, but I think soybeans was missing. In other words, I changed if you go into this area over here, I think there was one of these that didn't have any numbers in it or something like that. So I changed this to threes or something like that. Just make sure that there's every one of these groups has at least two values in it, is used at least twice.
So like, oh, so horse bean has one.
Yeah, I'll tell you what. I'll upload. I'll upload. Tonight, later on tonight, I'll upload another version of this file. So it's a problem with the number of. In other words, you can't have a group here that's missing values, or only has one value, for instance. Okay, it only occurs once. So I'll upload another version. I'll upload another version of the file. I corrected it on mine. I didn't correct it on the uploaded version. Okay. So I'll correct a matter of fact, let me save this now. I'll save this version. I'll call it 2. I'll save it and I'll upload this afterwards. Okay, I want to move on to homework 5 because we had some issues with that last night. I want to go through that as quickly as possible. Okay, so citywide, the population, the investigator wishes to test if the SATs of the first year psychology majors are different than psych majors. So state your null and alternative hypothesis. I meant this to be radio buttons, right? So the null hypothesis is mu population equals mu psych students. I meant this not to be radio buttons, to be boxes. So you would choose this one and this one for your null and your alternative hypothesis. Okay, so if you chose one, if you chose mu equals, if you chose the first one, it'll be fine. It'll work right.
What do you mean? This is 5B?
This is 5B, question 1. Just ask you to I'm going to change this to just say state your null hypothesis. Calculate the standard error for the means of sample size 100 for a psychology major. Well, what is our standard deviation for psychology major? Standard deviation was 100. Okay, and our sample size was 100. So our standard error is going to be 100 divided by the square root of 100, which is 10. So our standard error is going to be equal to 10. I think, is that right? Okay, determine the critical value of t. You choose based on whether the population sample is of that. Well, we don't know the population standard deviation, do we? Did I give you?
No, the sample deviation.
Yeah, only the sample standard deviation, right? Okay, so your critical value of t for a sample size of 100 would be 1.98, right? Okay, calculate the t-value for this hypothesis. Okay, it's a two-sided hypothesis test. Okay, let's see. Okay, in other words, alpha is going to be 95%, 5% rather. So we're comparing 600 to, let's see, 624. So it's going to be 624 minus the known mean. It's a single sample test, two-sided, but two-sided probability, 2.5% on each side, not single-sided. But it's going to be 624 minus 600, which is 24, divided by the standard error you calculated, which was 10, so it's 2.4, right? Is going to be the value of t that you calculated. Your critical value of t was 1.98, right? So calculate the p-value for this hypothesis test. Two-sided pi. So you can use Excel to calculate that. Okay, p-dist. Let me see if I can get Excel up here quickly. Okay, p-value. If I use Excel to calculate it, it's going to be equals t-dist, parentheses, and I put in the value for t, which is 2.4, the one that I calculated, comma, the number of degrees of freedom, which was 99, right? It was 100, the sample size was 100, comma, the number of tails. In other words, one-sided or two-sided. If one-sided, it'd be a 1. But most of these, two-sided significance. A lot of times in SPSS, you'll see two-tailed or two-sided for the answer. Okay, so it comes up to be 0.018. The probability of being wrong if you reject your null hypothesis is 0.018. Okay, so number 6, based on the above, would you accept your null? You're going to reject your null hypothesis and accept the alternative hypothesis. Okay, so let's go to the problem that kind of chewed everybody up. We have two samples here. We have a sample of two groups of women. One group that smoked. Okay, there were 77 women who had babies that smoked, and there were 161 women who had babies, mothers that didn't smoke during pregnancy. And they measured the bone mineral content for each one of the two mothers. Each one of the groups had a different um, uh, uh, standard deviation. They were pretty close, right? 0.026 versus 0.025. Numbers a little unwieldy. Assume that the variances of the underlying populations are equal. Well, we would have done that anyway because they're so close. Okay, state your null hypothesis. Well, it's going to be the mean calcium density, bone density for smokers' babies is equal to mean density for non-smokers' babies. Your alternative hypothesis is that they're not equal. Okay. Calculate a pooled standard deviation for the two groups. That's question 9. Then calculate the standard error. Actually, this little hint could have gone up into number 9 because it's the calculation for pooled standard deviation. Okay. Then calculate the t-value for the difference between the two means. And then compare it to the critical value of t to decide whether you can accept whether you can reject the null hypothesis. Just a quick note here. You never accept the null hypothesis. You fail to reject the null hypothesis. Just because you didn't have enough evidence to reject it doesn't mean that you accept it. You have no conclusion on it. You just fail to reject it. Okay, so let's go ahead and actually do this calculation. And I'll come out to that.
Which one are we doing now?
Number 9, yeah. Okay, so that was the whole group, the whole group of that. First of all, this is we decided that because the standard deviations are so close, and they gave it to you in the problem, that the variance in these two groups are equal, right? 0.026, 0.025. So I've summarized the data here for smokers and non-smokers, the sample sizes. Okay, so what do we use here? Well, we're going to use the formulas from that chart, that table, which are summarized here. That the top of this, the difference between the two means, divided by the standard error, is our t-score, right? Now, the only problem is that this is a little complicated here because before you can do anything else, you have to calculate this pooled standard deviation, right? So I'm going to solve this problem step by step, okay? So the first thing I need is the pooled standard deviation, right? Which is I just took the formula. This is the formula for the pooled standard deviation right here, right? So I want to actually do that calculation. So there's a lot of stuff going on in there, so I'm going to do it step by step. First thing I'm going to do is this part over here. I extracted it here. This is equal to the sample size minus 1, which is equal to 76, right, times the standard deviation of that group, which was this number here, 0.026. And it comes out to that. Now I'm going to do the same thing for the second part in here. Equals 160 times this standard deviation for group 2. Oh, I'm sorry. I made a mistake there already, didn't I? Right? That was supposed to be squared, right?
Yeah.
Yeah, so let me go back there and hit squared. Do it twice. And this one is this one squared times this again. Okay, so it's 77 times 0.026 times 0.026. And this one is 160 times 0.025 times 0.025 squared. So now I have this number and I have this number. Now, what about the bottom number down there? Well, actually, first, let me add these two together. Okay, so this is going to be equal, the top part here is going to be equal to those two numbers added together. In other words, it's going to be equal to this plus this, okay, which comes out to 0.15. Well, now I need the bottom part here. The bottom part is going to be n1 minus n2, which is going to be equal to 77 plus 161 minus 2. Okay, 236. So now I'm ready to do my calculation, which is, first of all, this is the bottom of the equation, right? And this number is the top of that equation, of that fraction. Okay, so now I'm gonna calculate my pooled standard deviation. It's equal to the square root of this number divided by this number. Okay? 0.025. That's what I wind up as my pooled standard deviation. Notice it's between these two values because it's basically a weighted average. If it's not between those two values, you know you did something wrong. Okay, so now I'm going to go ahead and I'm going to solve the rest of this problem. Well, first, I still need to find the rest of this bottom of this equation, which is basically the standard error. So in order to solve that part now, I have to figure out what the pooled standard deviation times this quantity is. Well, I'm going to take that inside part there, that 1 over n1 plus 1 over n2. So I'm going to say it's equal to, parentheses, 1 over 77 plus 1 over 161. Okay?
What, this is question.
This is the rest. See, pooled standard deviation. Look up. Pooled standard deviation times the square root of 1 over n1 plus 1 over n2, the two groups. Sample sizes of the two groups.
And what's this gift? This is
because I got to calculate the bottom here, right? All I've calculated so far is this SP, the pooled standard deviation, using this formula. Before I can solve this, I have to calculate SP. So that's what I did here. I calculated the pooled standard deviation.
okay.
Right?
0.025.
Yeah, what was the question?
So are you on question 10 now?
Yes.
Okay.
Okay, so now it's a continuous process, right? We're calculating all of this. So now that I calculated the pooled standard deviation, now I have to calculate this part in order to get the whole bottom of this equation, the standard error, which is the bottom half of this equation. So first thing I'm going to do is I'm going to calculate 1 over n1 plus 1 over n2, and that comes out to that number. So now I need the square root of that. So I'm going to say is equal to the square root of this number. Okay, so that's the number. Can we do this only if you have the data files, right? If I give you the data file, you can do this in SPSS. Yes. Okay, so now now I'm ready to calculate this whole bottom part here. And what is it equal to? It's equal to the pooled standard deviation. Where is that? That's down here, right? Times the square root of 1 over n1 plus 1 over n2, which is this number here. So I get 0.0035. Now I'm ready to actually do my calculation of my t-score, but I still need the top part, x1 minus mean 1 minus mean 2. So that's equal to, mean 1 was 0.099 minus mean 2, 0.091. So this is the bottom of my equation for t. This is the top of my equation for t. So let's go ahead and do that calculation. So our t-score is equal to 0.08 divided by the standard error, 0.0035. So I wind up with a t-score of 2.2797. Can I reject my null hypothesis? Well, in order to know if I can reject my null hypothesis, I have to compare it to t critical for this sample size. Well, for equal variances, right, the way we calculate the number of degrees of freedom is equal to n1 plus n2 minus 2, which we already know is 77, plus 161 minus 2 is 236. And what is t critical for a sample size that big? Well, it's going to be like 1.97. It's going to be very close to 1.96. I could go to the table. Table only goes up to 100, and at 100 it's 1.98. But in any case, whichever one of those that I choose, my t-score that I calculated based on how far apart these means are is 2.27. The t critical is 1.98. Can I reject my null hypothesis? No. Yeah, I'm with you, Vicky. I would use about 1.96. No, hang on a second. My t-score is bigger than t critical. right? The standard error is this entire bottom half of this fraction, and that came up to be that number. That's my standard error. And this is my x bar 1 minus x bar 2. Okay, top and bottom half of my equation. So my t score is bigger than my t critical. The means are further apart than I need them to be to reject the null hypothesis. So I can reject the null hypothesis and accept the alternative hypothesis, right? Because this is bigger than t critical. If it's bigger than t critical, what does it tell you about the p-value?
Smaller.
It's small. By necessity, the smaller the p-value is less than 0.05. If we did this in SPSS, it would have calculated it for us.
So wait, the t-score is bigger than the t-critical?
Right. So we reject our null hypothesis. The t-score tells you how far apart the means are in terms of standard errors. So the further apart the means are in terms of standard errors, the less likely they will have come from the same populations with the same mean. So the bigger that t-score that you calculate it, you get is, the more likely you're right to reject the null hypothesis. The less likely you'll be wrong if you reject the null hypothesis. So you want that t-score to be bigger than your t-critical. Your t-critical is the smallest t-value you can use to reject your null hypothesis. In fact, the t-critical, not by coincidence, but because that's the nature of this whole thing, the t-critical represents a p-value of exactly 0.05. So if you have a t-score less than t-critical, your p-value is more than 0.05. If you have a t-score that's more than t-critical, your p-value is less than 0.05. Both of them pointing to the fact that you can reject your null hypothesis. You can reject your null hypothesis if your t-critical, if your t is bigger than t-critical, or if your p-value is less than alpha 0.05. Okay, I'm going to save this sheet right now and put it online. And I also have one on the other side where if you want to do it for yourself, you can go step by step. This is this step, this is this step, to do it with unequal variances. Now, just because the right way to do this one is equal variances doesn't mean you can't give this a try with the same numbers over here and see if you get a difference or something like that. In fact, the numbers here are so far apart. The means are so far apart that like you'll also reject the null hypothesis here as well. Save as 5B11 demo.
You can use this on the test.
Yeah, yeah, absolutely. Demo.
Are we gonna have to calculate by hand on the test?
You can use Excel, or you can use a calculator. If I ask you to do something like that, it's going to be much simpler calculation than this. It's not going to be as bizarre numbers as this is. So I gotta let me explain to you why some of you guys had different answers than I did. They were close but different answers, like 2.35 or 2.32 or something like that. If, for instance, if I take a number like 8.5, right, and I say, I could round that up to 9, or I could round that down to 8. Okay. One of the things that we did here was we squared things, we took square roots. If I take 8.5 and square it, what do I get? I get 72.25. Well, if I rounded it up, what would I get? I would get 81. If I rounded it down, what would I get? I would get 64 when I squared that number. When you take a number and you take it through several processes, if you round it at the beginning, by the time you get to the end, you've multiplied the errors that were introduced by that initial rounding. So I understand that you don't want to necessarily type this into your calculator, or this, so on and so forth, or this into your calculator, or this into your calculator. But if you round it, you have that potential. So you should at least maybe carry 4 digits or something like that. But for the test and for this homework, I already did it on the homework. I'm going to make the range wide enough that if you use a calculator and you do a little bit of rounding, you'll get it'll grade it correctly. Plus, I always go back and look at them anyway. Yeah, with standard it's squared, right? S1 squared, S2 squared. So it's N1 minus 1 is 77 times 0.026 times 0.026.
Can you go to
Question
question 15?
15, what's
I
question
only got
15?
one wrong, but I
Oh
can't
my
figure out.
goodness.
It doesn't tell you which one.
The
It's
mean
4
gestational age of, oh yeah, let's see. The mean gestational age of infants born to mothers who smoked compared to mothers who did not smoke resulted in the t-value for this analysis was 2 point, what was it again? 2.27.
I can't see
The t-value.
we base it on that, no on the table right below it.
Oh, I'm sorry. Yeah, you're right. Okay, so yeah, that's kind of hard to read. The t-value for this analysis is, well, equal variances, right? Where you're going to use the top line because there's equal variances. The t-score is 4.476, right? With a p-value P-value is 0.000 or 0.001, probably less than 0.001 or 0.000. The total size of both groups is, well, a lot of people, it's 100, right? A lot of people put 98. I'm going to spread that out. Yeah, you could add up the samples. You can add up 21 and 79.
So what, it's 100 or?
It's 100, yeah. Sample size. The degrees of freedom is 98. So that's a little bit tricky, I guess, right? Based on this result, we would reject the null hypothesis. Okay, so the only tricky thing here is I think is the sample size because I should have said degrees of freedom. Right. Okay, so I'm gonna call it a night at this stage. And what I'm going to suggest is I can go on for like maybe a half hour tomorrow night. I'll set something up, but try and email me specific questions. I'll try and address specific questions tomorrow night. What's dinging here?
That was my thing.
Oh, okay.
On question 14.
Yes.
We accept the null hypothesis?
On question 14, we reject the null hypothesis because remember what was the t-value that we calculated? No. The t-value.
No,
t-score.
Question 14. It says 0.607.
On question 14, the p-value is 0.000, significance. Oh, I'm sorry. Hang on a second. It's a different question than one I just answered. Based on this result, 100 males, based on this result, the t-value for this test is, I can't read it, it's like 0.67 something, right? It's a small number, 0.6 something, right? 0.607. Based on this result, you should, the two, obviously, take care, right? Are they equal or unequal variances? Right? Well, because the significance here for this equality test of equality of variance is bigger than 0.05, we say that they're equal variances. We stay with the top line. The t-value for this test is 0.6 something, okay, which is a small value with a p-value of 0.545. So 0.545 is bigger than 0.05. So we fail to reject the null hypothesis for that question 14. Right? You comfortable with that?
Yeah.
Right? The t-value is way less than the critical value of t, right? Which would probably, for a big sample size, would probably be pretty close to 1.96, right? And the p-value is way bigger than 0.05. So there's more than a 5% chance we'd be wrong to reject the null hypothesis. Okay, I know it's confusing. Yeah, Carrie, it's on my screen. I'm looking at a laptop here with a 10-inch screen, so it's really hard for me to read it on here. And SPSS is not it doesn't behave. This preview, actually, I should be able to. There it is. Should be able to zoom in. Yeah, I thought I was an SPSS there for a moment. Yeah, there you go. Okay, so the t-score is small, so you fail to reject, but that's also because the p-value, the significance, is greater than 0.05. Both of those are indications that you failed to reject the null hypothesis. Okay. Okay, guys, so let's call it a night. Email me, or better yet, post questions in the discussions board, and I'll go on for a little while tomorrow night, and we'll try and answer any of the questions that are still hanging out. Okay? Okay, so good. Oh, by the way, I'll also add this to Blackboard. There are, on this particular site, there's a pretty good summary on the single sample t-test, when to use it, and what the formulas represent. And similarly, there's also, same site, paired sample t-test, the formulas. Right? And similarly, so on and so forth, independent samples, and even one for analysis of variance. Okay, so I'll put those links up on Blackboard tonight. So good night, guys.
Thank you.
Take care, eh?